Imagine injecting millions of tons of carbon dioxide underground and believing it will stay trapped safely for thousands of years for our decarbonization goals. What if studies have shown that the simulation models to predict that behavior contains flaws due to oversimplified assumptions? Good day everyone, I am Edmund from Universiti Teknologi PETRONAS taking Petroleum Engineering, and I will share on the uncertainty framework to improve the reliability and safety of carbon capture and storage projects. So, to kick things off, the world is rapidly undertaking decarbonization efforts to achieve net zero targets, and CCS has emerged as the technology moving forward to decarbonize heavy industries such as manufacturing and oil and gas. The simple idea of CCS is to gather carbon dioxide from emission sources and inject it back to subsurface geological formations for long-term storage. With that, it introduces a somewhat complex relationship between the injected supercritical CO2 with the native brine within geological formations. Their movement is governed by the concept known as relative permeability, which has been treated as deterministic and static, although studies have proven that underground CO2 does not behave in one predictable way. This is further compounded by different rock layers and issues like uncertainty in parameters that can completely change the injectivity, pressure buildup, and trapping for long-term estimation. With that, this study aims to develop a framework that incorporates uncertainty quantification to CO2 brine relative permeability models to control safe CO2 storage. This is achieved by multiple objectives, which includes the characterization of parameter dominance across time regimes for overall project risk assessment, the effect of neglecting realistic flow physics known as hysteresis, and the compounded effect of geological simplification through screening level bias quantification. The innovation of this study does not lie in the discovery of new physics, but more on the exploration of the parameter shift across time regimes as outlined by existing literature study. To put it simply, what controls injectivity at the beginning of CCS projects is completely different than a parameter controlling long-term storage at the end of simulation. Therefore, this study transforms CCS feasibility evaluation entirely for more secured projects. The foundation of the study is subsurface reservoir simulation while making it uncertainty aware. First, key CO2 brine flow parameters were collected from experimental literature, and the probabilistic uncertainty ranges are generated using Latin hypercube sampling to characterize the input uncertainty. Then, three progressively realistic reservoir systems were simulated, from simple homogeneous to real fluid flow behavior in form of hysteresis, and finally, a geologically layered heterogeneous system. The CCS project was modeled at 30 years cyclic injection, followed by a period of 970 years of trapping monitoring to capture both injectivity and long-term storage security. The core findings of the study was that parameter dominance changes with time. As shown by our Spearman rank sensitivity analysis, gas mobility controls injectivity during early injection, while hysteresis controls the flow of CO2 inside reservoir during cyclic injection, and residual trapping coupled with geological layering controls storage security at leak time. So the story here is straightforward. The CO2 flow in reservoir transitions from mobility limited to structure limited, and highlighting the regime-dependent nature of CCS behavior. To further support the findings, this study deduced that long-term trapped CO2 was underestimated by 39% median difference when neglecting hysteresis modeling. Additionally, while geological simplification reduces computational burden, it actually overestimates simulated injectivity by up to 50%. This proves that simplified models can produce misleading storage forecasts, which this study successfully addresses. The findings of this study also complements existing works while bridging the gap between computational efficiency and flow realism. Therefore, not only this study introduces novelty in the form of quantifying the bias due to physics neglection and developing the uncertainty framework for CO2 brine models, this study directly supports safer CO2 injection strategies and more reliable storage verification that translates into operational balancing. This ultimately paves way for more efficient CCS project feasibility and aligning with global SDGs in safely achieving decarbonization ambitions. In conclusion, this study has demonstrated the dynamic nature of CO2 brine relationship in subsurface, where reliable CCS assessments cannot rely on static assumptions. By developing an integrated CCS assessment model that is highly reproducible, this study contributes to the future of safer carbon storage projects. When storing carbon for thousands of years, understanding its true and accurate behavior is no longer optional, but it becomes the foundation of storage security and long-term goals. That's all for me. Thank you.